Today I wanted to go over some examples with one-dimensional motion. I actually have time today for homework questions if you have them. With that, let me just do one example before you ask any questions, and it'll be time to think of them. So here's an example. Let's suppose that you, I don't know, you got Mr. Top Hat. All right. And let's suppose he throws a ball upwards with an initial velocity of, I don't know, 100 meters per second. Not too shabby. And let's suppose he throws it from a height of, yeah, I don't know, let's say 10 meters.
He is tall.
Yeah, this is a, he's maybe one of C.S. Lewis's space trilogy. Tall people. All right. Okay, so this is on Earth, and so what happens, of course, is it goes up, and then eventually it comes right back down, right? So we can ask some questions about that, right? We can ask questions like, what's the the maximum height the ball gets to, and we can also ask, at what time does it hit the ground, right? Now, basically, this is what kind of motion? This is constant acceleration motion. It turns out that the force of gravity close to the surface of the Earth basically gives you a constant acceleration downward of 9.8 meters per second squared. So the acceleration is equal to minus g, which is minus 9.8 meters per second squared. All right. So again, our goal, find max height and find time until it hits ground. All right, so we'll think those are our goals to figure out those two things. So basically, we'll just use the equations we derived last time as they apply to this particular problem and see where it takes us. So let's see here to start with. I know that the velocity at time t is equal to, well, it's equal to 100 meters per second, right? Minus 9.8 times t. Well, I'm going to be lazy here, if you don't mind. I'm going to erase that meters per second, and we're just going to work in implicit units of meters per second as to avoid writing a bunch of multipliers all over the place. This will be okay as long as I stick to meters in seconds and don't all of a sudden throw into centimeters and blah, blah, blah. Okay, anyway, so 100 minus 9.8 t. That's the velocity at time t, right? Let's see here, what else can we say? What's y as a function? Y, let's see here, y. Well, at time 0, which I'm assuming is the time when the ball is thrown, right? Y0 is 10 meters, right? But I'll just write 10 and understand that y is in meters. That's its initial position. What's its initial? So then plus what? Plus 100 times t, because it's going 100 meters per second up to start with. And then minus 1/2 gt squared, right? Which is that's what minus 4.9 t squared. So I'm just putting specific constants into the constant acceleration formulas we derived last time. There's y as a function of t. Pretty much all I need in order to figure out the answers to the questions I have there. All right, so to start with, let's work on the max y. What can you say about maximum y? We have t max such that what? Yeah, you could use calculus, but let's use intuition. We have the time max such that what? V of the max time, the maximum height is 0, right? What comes up must come down. When the y velocity is 0, that's when you're at the maximum height, right? Of course, we could derive that with calculus. Don't worry, I will do calculus. I will not disappoint. But we don't need to do that here. So that's just what? 0 is equal to 100 minus 9.8 times t. So that tells me that the time to the lucky max, as I give it a label, time at the max height is equal to 100 divided by 9.8. And we'll put units in seconds, all right? It's going to be in seconds. I'm thinking in future semesters of only doing examples from Earth 2. In my hypothetical Earth 2, g is 10 meters per second squared. But, oh well, I will suffer the calculator. Okay, so 10.20 meters, meters, what's wrong with me? Seconds, a little bit more than 10 seconds, all right? Okay, great. That's not what I asked for though. What I asked for was the y max. So to figure out y max, what do? I just say, okay, y max is equal to y at time, just evaluate the formula at that time. So I plug in times 10.2 into my formula. So I get 10 plus 100 times 10.2 minus 4.9 times 10.2 squared. So what do we get? I got 520.6, but that could be round. I mean, we might agree. It's just a question of how we put it in the calculator. So 520.6 meters is what I get. There you go. That's the maximum height. That's it's pretty tall. It's like 5 football fields straight up. Yeah, that's like there's 1,600 meters in a mile, roughly speaking, right? That's like a third mile straight up. Right. So, but I guess if you could throw 100 meters per second, that wouldn't be such a mysterious thing. I mean, can you throw 100 meters per second? Not without technology, yeah.
I got this.
So yeah, if you've got a gun, you probably can do it.
She's got to lift a lot.
The bullets! Okay, so the next question that we have to answer is, so we got the max y, right? Now we were supposed to find the time. So how do we find the time?
But twice the amount y max for y.
Now that would be incorrect because that symmetry is not present here. See, he's saying just double the max time. If I had thrown it from the ground, yeah, that'd be fine. But I didn't. I threw it from 10 meters up. So there's an asymmetry between the up and the down. I can't just double the max time.
But you do know the total displacement for the second half.
Yeah, there is probably a variety of different ways you can do it, but here's a simple way. We're interested in this right here. What time is this, right? T equals what? Yeah, what's the final? When is that? What time is that? Well, what can you say about y there? I mean,
Y is 5.
yeah, y is equal to 0 by by the equation. By the equations I wrote, you should pick up on. If I say y equals to 10 is where you threw it, that means y equals 0 is the ground, right? That was implicit in my conventions from the start. So all I really have to do is solve a certain equation, right? So to find total time, t, just solve 10 plus 100t minus 4.9 t squared equals 0. You're like, oh no, but sometimes I can solve that kind of equation, and sometimes I can't. Incorrect. This is a quadratic equation. We own these, right? You can solve any quadratic equation with this thing called the quadratic formula, right? Now if I was in calculus, I would have said something like, you should complete the square. But this is physics, so I will tell you, use the quadratic formula. But use it carefully. So t is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. All right, so I got to identify what the b and the b, what's b, what's a, what's c. basically here, A is equal to minus 4.9. B, the coefficient of T is 100. The coefficient, the constant term is 10. Right? Okay, so what I have then is I've got minus 100 plus or minus the square root of 100 squared minus 4 times minus 4.9 times 10 divided by 2 times A, which is, by the way, minus 9.8. Of course, it could be that this has no solutions, no real solutions, right? If that was the case, that would mean that there is no such time, right? But that won't be the case here, because the thing inside the square root, the discriminant, in fact, is positive, right? So, I guess if I was lazier, I could actually figure out how to use the built-in quadratic solver in this. If I was in your place, I certainly would. You know these calculators have quadratic solvers in them, right? You can put the coefficients A, B, C in, and it will give you back the answer. That exists. Oh, did I allow you guys to use graphic calculators?
Yeah.
Oh, man. I was talking to me, I was thinking maybe we should start just bring your laptop to the test and what's the difference?
Great idea.
Oh, man, I just lost my number. You guys do that to me more. Third squared. In the interest of me being able to get partial credit on this, let me write out my work. This is the square root of 10,196. Which is 100.97. So I've got minus 100. Gotta be careful. The round off error could get you here. 100 point. I will keep more than four numbers here. I'm going to keep 6, 9, and 5. Let's see here. So what's that? What? Oh, no. Really? I did something screwy. I mean, I don't like my number. What'd you guys get?
I'm getting the same thing as you.
20.5 seconds?
20.51.
What, you said 20.5? 20.5 I like. So, okay, so you got 20.5 and what else?
It's like -0.1.
0.1. Okay, so this corresponds to what?
Before you throw it.
Before I threw it, right? Mathematically, the math cannot tell the difference between me throwing the ball with a speed of 100 meters per second at 10 meters and somebody else sitting in a hole and throwing it from the ground with a higher speed such that it decelerates to 10 meters, 100 meters per second when it reaches that height. Like the math is the same. The math doesn't really have t equals to 0. Is t equals to 0 really in these equations? No. You can follow t negative, right? And it will just basically extrapolate backwards. So you say, well, then the math is wrong. Well, yeah. But we use common sense to throw out this solution, right? That's not a physically relevant solution. Obviously, 20.5 is what we're looking for. So total approximately 20.5. At least you guys can use the calculator. That's good. Now, the doubling the time is pretty close to correct here, right? Because it's almost symmetrical, right? I mean, compared to it goes a third of the mile up. It goes a third mile up, right? So that, compared to the 30 feet it is off the ground to start with, it's not a big deal. So it's almost true that the total time is double the time up, but it's not. Yeah.
So using this method, if we were given point the velocity and location of the ball, say halfway up, would you ask us how fast it was going when it was launched at ground level?
I could. We can ask many questions. I mean, if you asked me for a list of the questions I might ask you about these things, that I could not give you. Although I did give you a list of questions to do. So, I mean, I kind of tip my hat a little bit about what I'll ask you about there. But all right, well, anyway, I hope you enjoy this. Some important themes, the quadratic formula. You need to be able to apply the constant acceleration formulas in specific contexts. That's kind of a big deal. So with that, are there any questions specifically about a particular web design problem that you're stuck on? Yeah.
Though there's one where it's constant acceleration, car on and on ramp, being on starting from 0, ending at a certain speed with constant acceleration, and it asks for the time it took
Right.
to cover that.
So here's the question. A car sits on an entrance ramp to a freeway waiting for a break in traffic. The driver accelerates with constant acceleration along the ramp onto the freeway. The car starts from rest, moves along a straight line, and has a speed of 30 meters per second when it reaches the end of the 120 meter long ramp. So let me draw a picture. Here's the highway. And then here's the on-ramp, basically. This distance is 120 meters. Right? We got a car. It starts right here. T equals 0 at rest, right? And then by the time it gets to here, at the end, car is going how fast? In my problem, 30 meters per second. I mean, it's randomized. You guys have different numbers. But I lost it already. Oh, here it is. All right. Now, what else are we told? It starts from rest, moves along a straight line, and it has a final speed of 30 meters per second when it gets to the end of the ramp, right? Which is about highway speed. That's for mine, it's 67 miles an hour. All right. So then the question was, there's a few questions that were asked. First, we're asked, what was the acceleration of the car? What is acceleration of car? What's the part B? The inquiry is, how much time did it take for the car to travel the length of the ramp? How much time? On ramp. And then part C is a question about the traffic flow. Part C is a question, okay, so if the traffic on the freeway was also moving at 30 meters per second the whole time, how far did the traffic travel while you were speeding up along the ramp, right? So how far did traffic go at that same speed, speed? It's matching the final speed, it matches the final speed. All right, so that's the problem. See if we can find a solution. So constant acceleration, right? So if I want to find the acceleration along the ramp, I know that the acceleration is constant. I know the final speed. I know the initial speed, right? And I know the distance. Well, what equation does that yell at you?
I don't know what the name of the equation.
I gave it a name last time. Yeah, the timeless equation. So we had df squared equals v naught squared plus 2a times the change in x, right? where a is a constant. So let's see here, the final velocity was 30 meters per second. So let's see here, this gives me 30 squared is equal to 0 squared plus 2 times the acceleration, I don't know, times the change in x, which is 120 in my problem. Bam. A is equal to 30 squared divided by 2 times 120. Now, at this point, I pulled the units back out of my hat, the magical hat that I put them in, because I do want an answer with units. You notice that I use meters per second, and I use meters. It follows that the answer will be in meters per second squared, because it's an acceleration. And again, you could do the math and clutter the calculation with meters and seconds squared all over the place. Some people would insist on that. I just don't care. Sorry. I grew weary of taking points off for it. Let's see. Okay, so 30 squared. And then once I stopped taking points off, I decided, well, if you guys can be lazy, I can be lazy, right? So let's see, 2 times 120. I mean, it's not like NASA's ever like wasted millions or billions of dollars on a unit conversion or anything. Let's see, 3.75. That actually happened. 3.75 meters per second squared. There you go. How many G's is that? G's is that? How many? So sometimes we'll talk about acceleration in terms of multiples of the gravitational constant, 5.8 meters per second squared. So if you were inclined to express this as in terms of G, what you would do is you take this answer and you multiply it by G divided by 9.8 meters per second squared, and that will get you. It should be less than 1. 0.3827. 0.3827 Gs. It's not utterly ridiculous. I mean, maybe your car could do that. I don't know. If this was like 5 Gs, I'd be worried. Unless you're driving a jet, you know. If you're driving a jet. But then while you're in the freeway, you know. I mean, Okay, next question. How much time on the ramp? I heard 8 seconds. How do you know that? The other equation? So VF is equal to V naught plus AT. Now we know A. So we've got 30 is equal to 0 plus 3.75 times T. So T is equal to 30 divided by 3.75 seconds. My apologies that my seconds and fives look the same. There's no fixing that now. Let's see here. 30 divided by 3.75, 8. As we were talking about it, 2 of you had said it, I would have known that it was right. There's only 1 I couldn't be sure. Okay, so next question. So how far does the traffic travel during this time? So if the traffic flow is at constant speed, then we go back to our middle school or high school physics where we had constant speed, right? 0 acceleration. And so the change in x for the traffic is just what? It's just 30 meters per second times the time. Look, I actually put units in. Aren't you proud? Okay, so 240 meters. There we go. Now, we calculate this stuff in our head all the time. As you're getting on a highway or something, right, you're thinking about all this. As you're getting on the merging ramp, you're thinking, where's that car going to be? When I get in the lane, is it going to be where I'm going to be? You know, we process all this stuff in our head, like real time, right? See? You should do well in the next test, you already know it.
Slightly.
Right?
Do it in the real world.
Or
Sit in the car with us.
hands-on.
Real world experience.
Are we gonna use your car for the test?
We're going to the car.
It's
Yeah,
a car test.
I don't know about that.
So like, if we don't crash, we pass.
Say for me, Lincoln.
Wicked is scary. Concur with
Yep.
heights.
Okay.
You like wrestling?
Yeah. Okay, so the gentleman has a question about problem 5. I guess I'll have Biddy on the camera woman and erase this and work again here. Camera lady. Okay, so gentleman asked a question about number 5, about the earthquakes and the P waves, P for primary pressure and S waves for secondary or shear. In the Earth crust, P waves travel about 6.5. So you got P waves, these guys travel, in my problem, about, let's see here, 6.5 kilometers per second. And then you have these S waves. How fast do they travel? About 3.5 kilometers per second. Pretty fast. Okay, the actual speeds vary depending on the actual particular material in the Earth at that place. Okay, so the time delay between the arrival of these two waves at a seismic recording center tells geologists how far away the earthquake occurred. So here's the question. If the time delay is 22 seconds, how far away from the seismic station did the earthquake occur? So here's my picture for this problem. Earthquake. Quack, quake, quack.
Quack.
And then over here, Mr. Top Hat has a seismometer or whatever it's called, and which let's just say he's put his ear to the ground and feels one. 22 seconds later, feels another. Okay. And so there's these two different waves. The one is the P wave, 6.5 kilometers per second. The other one, the S wave. But actually that's not the case, right? If I'm drawing it at the same time, it's not as far, right? So then it takes this extra distance. This takes what, 22 seconds to catch up with the other one. That's what we're told. All right, so how do you solve such a problem? Well, first thing you do is to write the things that you're given down, maybe draw a picture, try to collect your thoughts. That's what I'm doing. Every problem I work in here is like that. I draw a picture, I collect the data, I think about which physical equations are relevant, and then I go to work on the math. So here, I'm going to say this one is, let's say where the wavefront gets to, let's call it xp. Let's call where the wavefront gets to in the S wave as x sub s for S wave, all right? And so what's the equation of motion for the P wave? If I say that this is x equals to 0 for our convenience, right? Then x sub p is equal to 6.5 times what? T, right? And what's x sub s? Yeah, 3.5 times t. Right. Now, there's another thing I don't know here, right? Which is, what is this, I'm using XP as a variable, right? I mean, I didn't mean to say that XP is specifically this distance. Let's give that specific, the distance to the side, to the top hat here, a specific thing. I guess, for lack of a better thing, I'll call it X top hat, okay? So we have this, we have 6.5t is equal to X top hat, right? But we also have 3.5 times what is equal to X top hat?
T plus 22.
Yeah, exactly. So, two equations, two unknowns. Again, we own these, right? So it's just a matter of algebra, which you either can do or will learn how to. Let's see here. I think it's easy enough to eliminate X top hat for a second here. I mean, I'm really after t, so maybe I should. What should I do? I don't know. Oh, why don't I just plug 6.5 down here? So what I've got is 3.5. Oh, wait a minute. But I want X top hat, don't I? I don't know. Yeah, I mean, you can solve this in a variety of different ways. What do you guys want me to do? We're after X top hat, so I should probably eliminate t.
Or just solve it this way.
Yeah, stop talking about to solve it. I'll take that. Let's see here, t is equal to X top hat divided by, I grow it weird with my top hat. X, and I'm sure you guys by now are just writing X there. So X top hat divided by 6.5 is equal to t. Then just take that, plug it in over here, and then I get 3.5. I like your idea, just make it x. X divided by 6.5 plus 22 is equal to x. All right? And then solve it. You can do that because it's algebra. For my problem, I will tell you, it works out to 167 kilometers. You want me to actually work through it? I heard you reluctant, yeah. Let's see here. So I have 3.5 over 6.5 times x plus, let's see here, 22 times 3.5 is equal to x, which then gives me 3.5 over 6.5 minus 1, parentheses, times x is equal to minus 22 times 3.5, which then gives me x is equal to 22 times 3.5 divided by 1 minus 3.5 over 6.5. Which gives me 1,668.3. Or I'll just write 668 kilometers. Which, wait a minute.
I think it's something like 66 point.
What? Oh, I did 30. When I punched it in the calculator, I made that at 35. So, yeah. Human error.
Is that -0.9? So whenever when I did solve it back, I got 0.9.
I get 660. I get 166.83. All right. So this is, and by the way, the way to solve the runner on the track problem is kind of similar. whenever you're looking at intersection problems, right, you're looking for where two things intersect, what you essentially do is just write equation of motion for each and then set the positions equal where they match, and that allows you to solve these kinds of problems, whether they're at the same time or in this case at different times. So this isn't, I guess this isn't really an intersection problem, this is well, excuse me, this is not a collision problem, this is an intersection problem. We're looking for where these two paths intersect. They intersect here. I don't know how to say this, but shut up. Other questions? I don't know where to say about that. All right. At this point, I'm going to be lazy and show you a couple from my notes. You guys could. Thank you.
True law.
So I believe these are technically from lecture 4. Example 12 is the one we did at the start of class pretty much. I changed the numbers to protect the identity of the innocent or whatever, but I think this one was slightly less ridiculous, but
50 meters per second instead of 30.
That's
a little more.
I did 100 at class today, but anyway. This is a pretty complicated problem that I don't cover. This one is a better one to cover. Let's see if you do this one. All right, so here we go. Two stones are dropped from a cliff. The second stone 1.6 seconds after the first, all right? How far below the top of the cliff is the second stone when the separation between the stones is 36 meters? So if you don't know about kinematic equations I showed you last time, I don't think you'd figure out this question. I mean, I think you need math to figure this out, right? There's a subset of these questions I could have figured out as a third grader just through thinking, right? I didn't really need algebra. Just kind of adjust the answer and keep tinkering until you figure it out. Maybe not this one. So what I need then is an equation of motion for the top stone and for the bottom stone, right? I suppose that the B stone drops at time 0, and I suppose that the A stone drops at time 1.6, right? So what that means is for the A stone, the second stone that's dropped, I have to shift and reduce t minus 1.6 instead of t for the kinematic equation, right? But otherwise, they share the same initial height, right? They share the same acceleration, minus 9.8 meters per second squared. And you know, I also know that the time of, well, I know the time of flight is slightly different for them. I've set y equals to 0 here, the base of the cliff. Now, what are we given? The distance between the stones is 36 meters, right? That is going to be what? That's going to be ya minus yb. It's 36 meters, and what am I trying to find out? How far below, right? How far below the top of the cliff is the second stone when the separation between the stones is 36 meters? So what's this going to tell me? It's just going to tell me the time, right? So basically, when the difference between the positions is 36 meters, that's going to give me information about what time that happens at, right? Because I just take the difference of these two equations, then I can solve for time, and I get about 1.4936 seconds. Well, once I know that, then I can figure out that the distance that it's dropped, which would be ya minus y naught, which is 1/2 gt squared. Well, I just plug in this time, and bam, that's how far below the cliff is. That stone at that time. I never told you how tall the cliff was and all this. It didn't matter. Unsettling, yes? Maybe not. I don't know. A lot of problems were like that. we only give you partial information, right? But there's enough information that you can solve the problem. What's more fun is to give you more information than you need. That for some reason confounds the students more than anything else. Anyway, so there's a nice problem. I think this is not too far away from the idea of the flower pot and the windowsill problem.
That one is interesting.
This is kind of the same problem. This is a difficult problem. Oh, let's see here.
It's in the right place.
I know, I was making sure it wasn't too low. So, this question, I tell you, something. You have a subway car accelerates as it leaves the station. If it passes a certain person, this guy, waiting for another train, it takes 2 seconds for the first car to pass. And then it takes 1 more second for the second car to pass. All right? We're given that the cars have a length of 10 meters. All right? How fast are they traveling when they begin to pass? Nope, look at this. I mean, I've asked this in previous semesters. If you don't see this, trust me, if you try to use the other equations, like the ones we've been using so far today, it won't go well for you. This problem specifically is best solved with this average velocity formulas. So basically, the idea is just this. The average velocity over the first 2 seconds is what? How far does the train go in the first 2 seconds? It goes 10 meters, right? So the average velocity from time 0 to time 2 is 5 meters per second. But you know what else it is? It's 1/2 v naught plus v1. The average velocity is the average of the velocities. In the constant acceleration case, then the second car, we can apply this idea again. The average velocity in the second, from time 2 to time 3 is 10 meters. It goes 10 meters in 1 second, so the average velocity is 10 meters per second. But the average velocity is also the average of v1 plus v2, because that's the starting and the ending velocity during that time period from time 2 to time 3. Right? But then you can also think about it in terms of from here to here over that duration of 3 seconds, right? Over that 3 seconds, how far have you gone? You've gone 20 meters in 3 seconds. So 20 meters divided by 3 seconds gives you the average velocity over the whole first 3 seconds, which then gives me 1/2 v naught plus v2. So 3 equations and 3 unknowns is what is lurking in the shadows here for this example. So you have v naught plus v1 is 10, v1 plus v2 is 20, v naught plus v2 is 40 over 3, and you use some algebra and you find 5/3 meters per second. I don't know. This is a nasty problem if somebody doesn't tell you about the average velocity thing. Yes?
Are all these example problems on the super math website?
This is from lecture 4. So yeah. Oh, this is kind of not so much, this is a calculus example, which is nice, but this is more the sort of thing you see in differential equations. We may get back to this eventually. It's kind of out of place here in lecture 4. I just warned you about that. When you get to this one, you might kind of go, what? And that would be the appropriate response. Okay, so, oh, there's my offending diagram. Let's see here. See here if I have time for another one of these. No, I think that's it for today, folks. Have a good weekend. See you back Monday.